Hi again everyone, I'm Chris Tisdale and I'm a mathematician at UNSW in Sydney. And in this presentation I'm going to share with you an advanced study of ordinary differential equations. Now even though the ideas in this presentation are quite advanced, I've been very careful to ensure that the material is accessible to advanced undergraduates. And in fact, a lot of the ideas in here will be understandable to anyone who's done, say, 2 courses in calculus at university. In particular, the title of this presentation is Existence of Solutions to Second Order Boundary Value Problems Without Growth Restrictions. Okay, so essentially the presentation can be broken down into the following 4 subsections. I'm going to introduce and motivate the ideas. I'm going to present some sufficient conditions which generate so-called a priori bounds on solutions. Then I'm going to apply the ideas from section 2 to obtain some theorems regarding the existence of solutions to these boundary value problems. And then finally, I'm going to show you how to apply the ideas to some specific examples. So in particular, we're going to look at second order ordinary differential equations, or ODEs, with 2-point boundary conditions. Now I'll present some ideas involving what's known as differential inequalities to generate so-called a priori bounds on the first derivatives of solutions to the problem under consideration. Then I'm going to apply the ideas to produce some results concerning the existence of at least one solution to the boundary value problem under consideration. And the main tools involve differential inequalities, a so-called modified function approach, which is a general technique, and maximum principles. Okay, the ideas in this presentation are not new research. They're just nice, simple, special cases of general conditions called one-sided Nagumo growth conditions. But the nice thing about the ideas is that they're accessible to undergraduates. Okay, so I haven't tried to present the most general theorem as possible or the most general wide-ranging results. What I've tried to do is give people who are interested in learning a little bit about advanced ODEs a taste of what it's all about. Okay, so here's the problem under consideration. We've got a second order, possibly non-linear differential equation here, and we've got some 2-point boundary conditions. Now, the dash here is just meant to denote the regular derivative from a first course in calculus, and the same with double dash. One of the assumptions that we make throughout this presentation is that f is defined on this set, is real valued and continuous. Little a and little b are just points on the t-axis with a less than b. Capital A and capital B are just constants. Now, f doesn't necessarily have to be defined on this whole set for the ideas in this presentation to work, and I'll talk about that a little bit later. Now, if we sort of couple equation 1 with the conditions in 2, then these ideas are known as a boundary value problem, or BVP, involving 2 points, and in particular one with Dirichlet boundary conditions. So the main idea of this presentation is to study the qualitative properties of solutions to this joint problem. Now in the next section we'll look at so-called a priori bounds on the first derivative of potential solutions to this problem, and then we'll go on and actually present some ideas which give sufficient conditions under which these two problems, this combined solution. Okay, well the question is, why would you want to do that? Well, part of the general motivation of the study of boundary value problems and differential equations lie in the applications. Okay, we know that differential equations are very useful in modelling dynamical phenomena around us, and you can find some really nice examples of how differential equations can be used to mathematically describe lots and lots of different processes in these two books. Now, I'll show you these references at the end of the presentation. Now, if we know boundary value problems and differential equations describe a lot of physical phenomena, then it seems to make sense to also delve deeper into the theoretical aspects of these boundary value problems and these differential equations. And part of such a theoretical study involves the existence of solutions. And that's going to be the main focus of this presentation. Okay, definition to start off. What do we mean when we say a solution to our differential equation? Well, essentially, we've got to assume that f's continuous, and as such, a solution to our BVP is a continuously twice differentiable function, x, which is defined on this set and real valued. Now, I'm going to use the following notation for a C2 function, this kind of notation here. So this means that x is twice differentiable on this interval, and x double dash is a continuous function. So a solution to this boundary variable problem is such a function that satisfies the ODE and the boundary conditions. Okay, well, here is a little bit of history on approaches concerning the ideas that we're going to look at today and related ideas. One very important approach involved growth conditions, and this can be traced back to mathematicians such as Bernstein and Nagumo. Now, essentially, well, actually very loosely speaking, the growth conditions are on our f in the third variable, okay? And if our f satisfies such a growth condition, then these mathematicians went on to show that the first derivative of potential solutions to our boundary value problem satisfy what's known as an a priori bound. Now, we'll talk a bit more about that later. The obtention of such a priori bounds is really important in the theory of existence of solutions, and you'll see that when we look at the main result today. Now, this is the sort of growth condition that Bernstein introduced. So our f, our right-hand side of our differential equation, satisfies some sort of quadratic growth condition. Now, the a and b here is not the same as the a and b here. Okay, so if you find it confusing, say write these as say a1 and b1. Okay. So this is where the quadratic type growth condition or name comes from, I guess. Okay, well, Nagumo must have read Bernstein's paper because Nagumo picked up on this and generalised it. So Nagumo introduced the following condition. Well, f satisfies this sort of growth condition for some positive valued function h, and this sort of improper integral diverges. Okay? So these are two very, very important conditions, both Bernstein's and Nagumo's, that are used all the time in the existence theory for these two-point boundary value problems. Now, a good question here is, how can we replace the above growth conditions and still obtain a priori bounds on the derivative of potential solutions and also the existence of solutions. Well, this question has been researched by some of these mathematicians, Arco, Knoblauch and Schmidt, and their papers use geometric arguments and guiding functions. And another couple of papers that also researched this idea employed sign conditions on F with the method known as barrier strips. Now, if you want to learn a little bit more about those approaches, you can go and look up these papers, or you can have a look at this book and this paper, or this paper by Corman. They're very comprehensive coverage of these Nagumo, these growth conditions. Okay, so the search for a priori bounds on the first derivatives of potential solutions to the boundary value problem under consideration is very important, because once we have that knowledge, we then hopefully can use it in conjunction with other ideas to obtain the existence of solutions to our boundary value problem under consideration. In comparison with the previous and above works, this presentation is going to concentrate on sort of, I guess, weakening these growth conditions. Okay, and in particular, the F may feature unlimited growth in the third variable. Now, technically speaking, these ideas are known as one-sided Nagumo conditions. Then I'm not presenting them in their most general form, but the way I'm presenting it means it will be very accessible to those who are not experts in the field. Okay, so how is the presentation structured? Well, in section 2, I'm going to present some so-called a priori bound results for the first derivatives of potential solutions to the second order ODE, equation 1. And the ideas in the theorems involve really basic differential inequalities, inequalities that feature derivatives. In the next section, I'm going to apply the ideas from section 2 to gain theorems that ensure the existence of solutions. So the theorems from this section will involve sufficient conditions under which the boundary value problem under consideration will admit at least one solution. And finally, section 4 contains examples. So the first 2 sections are quite abstract, but the section 4 gives you some idea of how to apply these abstract theorems. Okay, so let's have a look at the first result. So let x be a C2 function on this interval. Let j, k and n1 be non-negative constants. If x has a second derivative that satisfies this inequality, and furthermore, these derivatives satisfy, at the endpoints of the interval, satisfy this inequality, then there is a non-negative constant, big N, which depends on these constants here, such that the derivative, the absolute value of the derivative on this interval is less than or equal to that N. Now, by these derivatives here, I just mean one-sided derivatives, so it's like a one-sided limit, if you like. Okay, so let's see if we can prove this. It's the case when j equals 0 is very easy. That's what I call the trivial case. The case where j is positive is the most interesting case. So let's see if we can go through and prove that. Okay, so firstly, if j equals 0, then essentially this disappears and you end up with these inequalities, and you can just integrate both of these inequalities from, say, a to t, and then form a second inequality and rearrange to get this. It's actually pretty easy. Now, if j is positive in this equation or differential inequality 3, then, well, this has got to be positive. This right-hand side has to be non-negative. So I can actually form this inequality. Okay? So what I can do now is integrate both sides of this inequality here. Once from A to T, and then the other from T to B. So this inequality, this interval of integration gives you this first inequality, and this interval of integration gives you this second inequality. Okay, now you can see here this and this are basically the negatives of each other. So we can actually combine these inequalities into the one inequality. And, well, covering the first case, that's our bound in the case j equals 0. And this is our combined bound for the case j positive. Okay, so this number n is known as an a priori bound. Now, note that in practice, little a is known, little b is known, big K is known, big J is known, big N1's known. Okay, these things are all calculable from the differential equation under consideration, assuming that these things hold, of course. Okay, so this will just be some number. N will just be some number. Okay, well, you can modify the proof of that, and instead of having this inequality here, you can have a negative sign, and where j is some non-negative number. Again, the non-trivial case is when j is positive, and then you can just follow the proof of the previous result through and get the same bounds. Now, if you really wanted to sort of steamroll lemma 2 and lemma 3 into one lemma, what you would do is you would just use this and say, well, j could be positive, negative, or 0. Okay? So if you want to sort of combine these, you could. You'd have to split the proof up into 3 different cases. So there are a couple of basic lemmas that we're going to rely on. Now, I'm going to introduce the following set, omega. Alpha and beta are going to be 2 special kinds of functions defined on this interval. Now, in particular, alpha and beta are going to be, like in our existence theorems, they're going to be C2 functions, and they're actually going to sort of pinch together at the endpoints of the interval. So they're also going to be well ordered. So think of this as a potential beta. Think of this as a potential alpha. You've got this region, set of points in between. And now if we add an extra dimension to that drawing, so imagine the positive axis is coming out at you from the screen, then what we've kind of got is this infinite set sitting in 3-dimensional space. Okay, so this omega is going to be very, very important. All right, so here's our one of our first a priori bound results. So let's consider our general boundary value problem, 1, 2, our Dirichlet boundary value problem. Let f be defined on this set and continuous on that set, and let alpha and beta be C1 functions on this interval that are well ordered, alpha is less than or equal to beta on that interval, with alpha and beta sort of pinching together at the endpoints of the interval. Furthermore, if there exist non-negative constants j and k such that f satisfies this inequality on the set omega, then all possible solutions to our boundary value problem that satisfy, or basically that stay between alpha and beta on this interval, also have a derivative that satisfy this a priori bound, where n is a constant involving all of these values here. So what does that say? Well, again, let's have a little picture. So suppose this is my beta function and this is my alpha function. Okay, so that's my beta up the top, that's my alpha down the bottom. So suppose f satisfies this inequality for some constants, j and k, j and k non-negative. Then for all solutions that stay in this set between alpha and beta, that solution has a derivative that satisfies this so-called a priori bound, where n is a calculable number involving these values here. That's what this theorem basically says. Okay, now we're going to rely on the previous lemmas to prove this. So let's see how we prove it. Okay, so suppose x is a C2 solution to our boundary value problem that stays between the alpha and the beta. Okay, well, if x is a solution, then basically x double prime equals f. So this then is just the following inequality. Okay, and that inequality was used in lemma 2 to get an a priori bound on the derivative. Okay, so if 6 holds and x is a solution to our problem, then x double prime has to satisfy this inequality here. If that's the case, then we can satisfy this inequality 3 of lemma 2. Now, the only other thing we need to have is this. Well, that's easy to satisfy as well. Since the alpha and the beta pinch together at the endpoints, and x is between alpha and beta, it means that x of a has to be equal to alpha of a, and x of a has to be equal to beta of a. And at the other endpoint, x of b has to be equal to alpha of b, and x of b has to be equal to beta of b. So what this means is that we can use a sort of a one-sided squeeze, pinching, or sandwich theorem, whatever you want to call it, to get these inequalities. Now, alpha and beta are one function, so these are well defined and they can be calculated. So we can form the following bound. Okay, so let's take the maximum of all of these 4 things, call it n2, and then whatever that n2 is, let's just define it as n1, and we can have this inequality 4 holding. Okay, so applying lemma 2, we know that under the conditions of the theorem 4, all solutions must satisfy, the derivative of all potential solutions must satisfy an a priori bound. And the bound is given by this. Sorry, that should be a j, not an a. Okay? So that's the end of the proof. Now, this may look quite abstract on a first viewing. It's not too bad to work with, but what we always try to do in mathematics is to present the simplest case if we can. So you can break this inequality down to the following very, very simple inequality. Okay, and in this lemma, it's claimed that inequality 6 will hold for some positive number j and some non-negative constant k, if and only if there's a constant c such that this inequality is satisfied on this set. Okay, now what does this say? It basically says that f has a lower bound, c, on this set omega. Okay, it's an if and only statement, so we got to, in order to prove it, we need to prove it both ways. So let's assume that 6 holds, and then what we want to do is show that there is a c such that this is true on this set. Okay, well, if 6 holds for some positive j, then, well, this has got to be, this right-hand side's got to be non-negative. Okay, so we end up with this, and then you can just take this to the other side and divide by j, and you get the lower bound on your f, where c is just defined by minus k on j. Okay, that was pretty easy. The second part of the proof is you assume this on this set, and then show that there is a positive j and a non-negative k such that 6 holds on this set. Okay, so there's 2 cases that I've discussed. If c is greater than or equal to 0, then this left-hand side has to be non-negative. So the absolute value of f is just equal to f on this set. And so 6 will hold with big J equals 1 and k equals 0. So that's that case. And slightly more involved case is when c is non-negative. Well, if that's the case, then just rearranging this, you come up with this. And then using the properties of the triangle inequality, you can come up with this is less than or equal to this, which is equal to this. So essentially rearranging this, bringing this to the other side, then you come up with this inequality here. So this will reduce to 6 with big J equals 1 and big K equals minus 2c. Okay? All right, so let's present some equivalent theorems, again stated very simply. Essentially, we make the assumption that f's bounded below on this set omega or above. Okay, so let f be continuous and that alpha and beta be C1 functions that satisfy this sort of ordering. And again, the functions pinch together at the endpoints. If there exists a constant c such that f is bounded below on this set omega, then all possible solutions to our boundary value problem that stay between the alpha and the beta also have a derivative that satisfies this a priori bound. Okay, so if you compare theorem 6 with theorem 4, this is a little bit more abstract than that. This is very easy to check whether it holds or not. So actually, from a practical point of view, theorem 6 is quite easy to use. Now, essentially this result is very similar to theorem 4, except here I've just got a minus sign out the front. Okay, so we still assume j is a non-negative constant, but we've got a minus jf there instead of a positive jf. Well, you can also just basically repeat the proof of theorem 4 and get this a priori bound on the derivative of all potential solutions that's claimed to exist. So I'm not going to discuss that proof. And again, similar to the previous few slides, instead of using this inequality, well, this inequality is equivalent to this inequality. Okay, so this assumption basically assumes that f's bounded above by some constant c on this set omega. Okay, so well, if this and this are equivalent, well, we can sort of reformulate or equivalently reformulate theorem 7 in the following way. Suppose f's continuous, alpha and beta are C1 ordered functions that pinch at the endpoints. If there exists a constant c such that f's bounded above on this set omega, then all possible solutions x in C2 to our boundary value problem that stay between the alpha and the beta also have a derivative that satisfies this a priori bound where n depends on these constants or these values here. Okay, so let's move on to section 3 here. I've spent a fair bit of time talking about these a priori bound results. Now what we're going to do is see how to apply them to generate theorems that guarantee the existence of at least one solution to our original boundary value problem. Now the ideas involve upper and lower solutions and so-called fixed point theory. Now I'm going to concentrate on the upper and lower solutions ideas rather than the fixed point theory. I'll leave the fixed point theory for another video because the ideas in there are quite deep. If I just concentrate on this, then the content in this video should be understandable by a much larger audience. So that's my aim. Okay, here's a definition. Consider the Dirichlet boundary value problem. 1, 2. Let alpha and beta be C2 functions that are well ordered on this interval. In particular, we assume that alpha is less than or equal to beta. We call alpha a lower solution to our boundary value problem if alpha satisfies the following inequalities. Okay, alpha double prime is greater than or equal to f of t comma alpha prime, and alpha of little a is less than or equal to big A, alpha of little b is less than or equal to b. Similarly, so this is alpha double prime here. Similarly, we call beta an upper solution to our boundary value problem if we just reverse the inequalities from here and just replace alpha with beta and alpha prime with beta prime, etc. Now these definitions are well known, and what we're going to do is use those to generate part of our existence results. Okay, so we call alpha a lower solution and alpha a beta an upper solution. So let me just draw a picture. So alpha and beta, this might be your beta, this might be, say, your alpha. They're well ordered, and this might be your big A, and this might be your big B. Now, in this definition, the ends of the alpha and the beta don't necessarily touch, but we will make that assumption in our main theorem. Okay, so I guess the assumptions on alpha and beta in this presentation are even stronger than what we've got here. Okay, now we're also going to rely on the following idea, very famous, very important idea of an Italian mathematician by the name of Scorza-Dragoni. Now, assuming this result means that I don't need to talk about fixed point methods or compact operators in this presentation. Okay, I'll leave the discussion of this result for another video. Suppose we have a function, big F, that's defined on this set, is continuous and uniformly bounded on this set. If those conditions are satisfied, then this boundary value problem has at least one solution. Now, what do I mean when I say uniformly bounded on this set? I mean that there's non-negative constant m, sorry, this should be r times r, so r squared here. So when I say f is uniformly bounded, a big F is uniformly bounded, I mean that big F, there's a constant m, a non-negative constant m, such that this constant bounds this on the whole of this set. Okay. Now that's a reasonably strong assumption. You don't come across too many differential equations whose right-hand side is uniformly bounded on this set. But that's not going to be a huge obstacle for us because we're going to modify, do a modified function method and actually get around it in a very neat manner. Okay, so I'll talk about this in another video, another time, and the proof. But this really is the main result of this presentation. So let's consider our boundary value problem, our Dirichlet boundary value problem 1, 2. Let f be defined on this set, let it be continuous, and let alpha and beta be well-ordered lower and upper solution. So alpha is assumed to be a lower solution to our BVP, beta is assumed to be an upper solution to our BVP, and alpha is less than or equal to beta on the interval of interest. And in particular, the ends of these upper and lower solutions clamp at the endpoints. If there exists non-negative constants, big J and big K, such that our F satisfies inequality 6 on this set omega, then our Dirichlet boundary value problem 1.12 has at least one solution, x, which is a C2 function, that stays between the alpha and the beta. Okay, so let me just put this into a little bit more context for you. Okay, so we're assuming that alpha and beta are C2 functions. Let's say this is your beta, this is your alpha, that are well ordered, C2, touch it at the ends of the interval, and that F satisfies inequality 6 on this set. What it says, what the conclusion of this theorem says is that there is a solution that stays between the alpha and the beta. Now, you could have more than one solution. The solution could pop out and then pop back into the this region between alpha and beta. We're not interested in those kinds of solutions. What we're interested in is showing that at least one solution lies between the alpha and the beta on the whole interval. Okay, so how do we prove it? This is the real main idea of this presentation. Well, we use the ideas that we've already seen in the previous section, and of course we're going to use this result, very important result of Scorza-Dragoni. Okay, so notice that we haven't assumed that our little f is bounded, but we do have a result if for a boundary value problem where the right-hand side of the differential equation is uniformly bounded. So what we're going to do is take this right-hand side and modify it so we do form a continuous and uniformly bounded function. Now this is done in the following way, and it's a bit, it looks a bit strange on first glance, so let's discuss it. Instead of worrying about the boundary value problem 1, 2, let's form a new boundary value problem where the right-hand side is continuous and uniformly bounded. Okay, so I can do this using a so-called modified function approach or modified function method. I'm going to define, in this context, big F to be the following. Okay, now I've defined it sort of on different regions here. You can see a big Q is going to be some number that's chosen out of the maximum of these three things. So N is the constant given in 7. I can calculate the max, given a C2 upper function, upper solution and lower solution, I can calculate these maximums and I can take the maximum of all three of these things and define it to be that Q. Okay, so you can see here that big F and little f are actually the same function on this set here. Now, outside of that set, so this is like, I guess it's like a three-dimensional bounded solid. Okay, the set is, and T's between little a and big A, of course, for all of these settings. Okay, so let's just try to go through this and break it down a bit more. If we go out of the sort of region between alpha and beta, what I do is I replace this second variable just with beta of t. If I go outside this big Q, I just in the third variable, then I just place big Q in this third variable, and then I've added something in here. Now, this something here is an extra bounded bit. Okay, it's not too hard to show that this is that there's a bound on here, no matter what this and this is. Okay, and same with here and here and here. Okay, so with a little bit of work, you can show that big F is continuous because little f's continuous, beta's continuous, alpha's continuous, and all of these things, these extra bits are continuous as well. And big F is uniformly bounded on the whole of T between little a and big A, the second variable, say P, in R, and little q in R. Okay? So now this is important. Our F is continuous and bounded, uniformly bounded on this set. Therefore, by theorem 11, this boundary value problem for this big F must have at least one solution. So that's really important. Okay, now what we're going to do, so you may think, well, so what? Well, what we're going to do is actually show that the solutions to this problem must lie in this set here. Therefore, in this set, big F and little f are the same. So if we can show that all those solutions lie in this set, then actually big F and little f are the same. So this then is our original boundary value problem. Okay, I hope that's clear because that's a very important point. Okay, so this is really important now. We show that all solutions to our modified boundary value problem must lie in this region. And therefore, in this region, big F and little f are the same. Therefore, the solutions that we've shown exist must also satisfy the unmodified or original Dirichlet boundary value problem. So how do we do it? Well, we want to show that solutions satisfy this and have a derivative that satisfy this kind of a priori bound. Okay, so I'm going to show that firstly, x lies above this lower solution alpha. Now to do this, we use maximum principles, and we're going to use the fact that basically alpha is a lower solution. Now I'm not going to show the case x less than or equal to beta because essentially the ideas are the same, but if you want to fill in the details, please be my guest. So I'm going to omit that case. All right, we apply an idea called proof by contradiction. So we assume that there's a t0 somewhere in the interval AB such that this inequality doesn't hold. In other words, the x of t0 is strictly less than alpha of t0. Okay, well, I'm going to introduce a function, r of t, just to be the difference of this. And r is going to be a continuous function because alpha is continuous and x is continuous. Now we're working on a closed and bounded interval. Therefore, this continuous function r must achieve its maximum value somewhere on that interval. Okay, so let's denote the maximum value of r as r of t0. And without loss of generality, we can assume that basically the maximum occurs at this point, t sub 0. Okay, well, let's go through a few different cases. If the positive maximum occurs at the endpoint, say the left-hand endpoint, then what this means is that r of a is greater than 0. In other words, alpha of a is greater than x of a, which is big A. And now this contradicts our assumption of alpha being a lower solution, basically because alpha of little a has to equal big A. Okay, so obviously t0 cannot be equal to little a. In other words, r cannot have a positive maximum at the left-hand endpoint of our interval. Now in a similar fashion, you can show that r cannot have a positive maximum at the right-hand endpoint. Okay? Well, what happens if the maximum value of r occurs in the interior of this interval? Well, we know from basic calculus that two things occur. Basically, the derivative of r must be 0 at t0, and r double dash of t0 must be non-positive. So, the first part says that essentially alpha prime of t sub 0 equals x prime of t sub 0, and this second inequality basically says that x double prime of t0 is greater than or equal to alpha double prime of t0. Okay, well let's start with this so we can form this. Now, because we've assumed that x is a solution to our problem, x double prime equals, our modified problem, x double prime equals big F. Okay, well, I'll get to this, I'll expand this in a minute, but using this, I can just replace x prime of t0 with alpha prime of t0 in the third variable. And if I go back to my modified function, the explicit representation, this is going to be the following, okay? It's a case where this, basically this is happening. Our choice of Q ensures that this, the absolute value of this, is going to be less than or equal to big Q. Okay, so that's why we can take this function, not this function in here. Okay, so going from here to here, you'll notice that we've assumed that this is negative because we've assumed that x of t sub 0 is less than alpha of t sub 0. Okay, so this, we can then form an inequality to get this, and we know because alpha is a lower solution, this is less than or equal to alpha double prime of t0. So what we've got now is alpha double prime of t0 is less than alpha double prime of t0, which doesn't make sense. So we reach a contradiction. So what this means is that t sub 0 can't be in the interior. So if we combine our cases, we know r cannot have a positive maximum at either endpoint of our interval, and it can't have a maximum, achieve its maximum value in the interior of the interval. So what that means is that basically r can't be positive at all. R's got to be less than or equal to 0 on this interval, and that's just the same as saying x has got to be greater than or equal to alpha on this interval. Okay, so similarly to the above argument, you can show that x has got to be less than or equal to beta. Again, the ideas are the same. Look at the endpoints, then look at the interior and invoke the maximum principle and the fact that beta is an upper solution. So if you combine those cases, you have x's between alpha and beta on this interval. Now the last thing we want to do is show that the derivative satisfies this inequality here. Okay, if that's the case, then our solutions will stay in this interval. F and big F are the same. Okay, all right, so how do we do that? Well, we show that big F satisfies inequality 6. So we want to show that big F satisfies this on this set. So we do that sort of in two parts. First of all, on this set, just using our definition for big F, you can show that big F satisfies the following. Okay, so we can write big F in terms of little f as this, and now by assumption, the assumption of our theorem, little f satisfies this inequality, and then you can sort of go back and go from here to get your big F again. So big F satisfies this inequality on this set, inequality 6. Okay, so let's just sort of flip this inequality around and show that big F satisfies the same inequality. Okay, if you do that, well, you can come up with the following. You combine the two cases, then you have big F satisfying 6. So what that means is that theorem 4 holds with little f replaced with big F. And what that means is that the solutions to our modified problem satisfy this a priori bound, and because Q was chosen, big Q was chosen to be bigger than n, basically x prime is less than or equal to n, so it's got to be less than or equal to Q on this interval. Okay, so we have shown now that all solutions to our modified problem satisfy these kinds of lie in this set. So big F and little f are identical, therefore the solutions to this problem must also satisfy the solutions to x double prime equals little f with these conditions, and therefore our original Dirichlet boundary value problem must have at least one solution that stays between the lower solution alpha and the upper solution beta. Now you can tweak that main theorem a few different ways. I'm not going to do the proofs, but essentially you can replace the inequality 6 with inequality 10, where basically you've replaced j with negative j, and you can form an existence result. You can replace 6 with the more simple inequalities like a lower bound on f on omega, or upper bound on f, a little f on omega, and you can still get the existence results. But I wanted to talk about a couple of examples now, just to give you a feel for how to apply these ideas. Now, let's have a look at the following boundary value problem. Now, you can see firstly, it's highly nonlinear, and the f grows in the third variable exponentially. So certainly this kind of f doesn't satisfy the classical quadratic growth condition of Bernstein or Nagumo. So certainly those ideas don't apply here. It's claimed that this boundary value problem has at least one solution. Okay, well, the first thing we're going to do is to see if we can choose an appropriate lower solution and an appropriate upper solution. Okay, well, in this example, I've chosen alpha to be just the zero function and beta to be 1 minus t squared. Okay, so you're going to get here's your beta, and say here's 1 and minus 1, and let's say your alpha is just the 0 function. Now, you can show that alpha and beta satisfy the differential inequalities of necessary to be a upper and a lower solution. Okay, so alpha is the lower solution, beta is the upper solution. Now, you can also show that on this set here, our f is bounded below by minus 2. Okay, so what you can do then is apply one of the previous theorems and conclude that there is at least one solution to this particular boundary value problem that lies between the 0 function and 1 minus t squared. Okay, now I haven't put all the details for that in. I'll leave you to put the details in for that. See if you can form the inequalities and check off that all the conditions are satisfied. But you can see that this is quite a nice conclusion, because it kind of gives us a location for where our one of our solution lies. It lies above this function and below this function. Now here's a second example. I've actually taken this, this example from a paper of Klaus Schmidt, and I've also taken the lower solution and the upper solution. But I just wanted to show that this kind of example satisfies the conditions of the theorems that you've seen in this presentation. Okay, so here is another boundary value problem. It's claimed that this boundary value problem has at least one solution. So in this example, I've chosen alpha to be t squared minus 1 and beta to be 0. So your lower solution is going to look something like this, and your upper solution is going to look something like this. And they pinch at the endpoints, and you can show that on this set, on omega, you can show that f is bounded below by 0. Again, you can apply the relevant theorem from earlier on to show that the boundary value problem, this boundary value problem, has at least one solution that lies between the alpha and the beta. Okay, but again, I'll leave you to put the details in and see if you can tick off all that all the conditions are satisfied. Now I'm going to leave you with some papers, some references. I haven't referred to all of these references. You can think of the ones that I haven't referred to as just some extra reading material. So here are some recent papers, both sort of from the last few years and also of a classical nature. So I hope you enjoyed this presentation. I hope I've given you a snapshot into advanced studies in ordinary differential equations, and I hope you can join me for more presentations in the future.